In this video, we're going to be finding the volume of shapes that are formed when we revolve curves around some axis, commonly known as solids of revolution. For this example, I'm going to show you what happens when we revolve this curve, cut off here, about the x-axis. So when we revolve a surface about an axis, it's no longer sufficient to be in 2D anymore, because in 2D, if we did this, all you would see is something like this, which isn't super helpful. So in the 3D plane, what's going on here is we are revolving around the x-axis. We are creating kind of like a trumpet, if you will, and our goal is to find the volume of this trumpet. But to see how we do that, we have to go back to 2D. Let's first think back to how we find area under a curve. Recall how when we looked at the Riemann sums and the limit process to finding an integral, we summed rectangles under a curve and we made them thinner and thinner and thinner and thinner until we got infinitesimally thin rectangles, which we represented as the integral. But for here, we can't use rectangles anymore because those are 2D. When going from area under a curve to a volume under a surface, we have to look at it a little differently. We have to find a shape that we can fill this solid with that'll encapsulate most of the area. If we use rectangles, that will only get the area of this plane, not anything else in this revolution. What we're going to do is, instead of summing rectangles, we're going to sum cylinders. It might be a little hard to see, but I filled this shape with a bunch of cylinders. And like how we made these rectangles infinitesimally thin, we're also going to make these cylinders infinitesimally thin like this until we're summing an infinite number of cylinders. But before we can sum them, we have to find an expression for the volume of one of these cylinders. We're going to start off with the simple cylinder volume formula and work our way down. This is the formula for the volume of a cylinder. And the first substitution that we're going to make is we're going to notice that this radius is equal to the height of the curve at x. And the reason I can say this is because when we take this revolution, this curve stays fixed. Or for every point on this x-axis, the distance from the axis to the curve doesn't change no matter which way you're looking from the axis. So we can say that volume is pi times f of x squared times h. But now we have to make a substitution for h in terms of something we can work with. Looking at this picture, what's h? H is this distance on the x-axis. So if we make this distance infinitesimally thin, we can call it dx, like this. And now we can sum the cylinders to show that the volume of a solid of revolution is pi times the integral of f of x squared dx. What I've just shown you here is called the disk method of finding the volume of a solid of revolution. And we use the disk method when we have something like this, where the area under this curve is such that at every point between A and B, a part of the area touches the axis of revolution. The second scenario we could have is when we have a shape like this, where the area that we're revolving does not touch the axis of revolution at every point in this interval. In this case, we have to subtract one volume from another. We're going to take the volume if we revolve the top curve around our axis, and then from that, we're going to subtract the volume we get if we revolve the bottom curve around the axis. This is really similar to finding the area between two curves, except now we're finding the volume between two curves. This integral is what you use to find the volume of when this area is revolved around an axis of revolution like the x-axis. And this is called the washer method. Notice that if we use the properties of integrals to split this apart, we have this, which is big volume minus little volume. Occasionally, you might also be given functions of y and asked to find volumes of solids like these. But if you get that kind of problem, it's not an issue because the formulas are the same for in terms of x and in terms of y. Since this is a particularly complex topic, I'm going to do 4 examples for you, 2 washer and 2 disks. Our first problem says we're going to find the volume of the shape that's generated when 2x squared between 0 and 3 is revolved around the x-axis. Let's first draw what this looks like. So here's 2x squared. I'm going to call this from 0 to 3. And you'll notice that our axis of revolution is the x-axis, and the area under this curve touches the x-axis at every point between 0 and 3. So we can use the disk method. The volume is pi times the integral from here 0 to 3 of our radius, or our function squared. So 2x squared squared dx. Evaluating this integral, we get pi times integral from 0 to 3 of 4x to the 4th dx, which is pi times 4/5 x to the 5th evaluated from 0 to 3, which is 972 pi over 5. For our second problem, we're going to find the volume of the shape generated when e to the x plus 3 bound from 0 to ln7 is revolved around the line y equals 3. So now notice we're not revolving around the x-axis anymore. We have our own axis of revolution. When I draw this, I have, here's y equals 3, and then here's e to the x plus 3. So here is 0, and I'm going to say somewhere here is ln of 7. So we see that this area that we have here from this curve to y equals 3 touches y equals 3 at every point from 0 to ln7. So we can use the disk method again here. But now we have to find our radius. And you have to be careful here. Our radius is not e to the x plus 3. Because if we use this, then we'd be finding the volume if all of this was revolved around the x-axis. But we're revolving this around y equals 3. So we have to find the distance from y equals 3 to e to the x plus 3. The easiest way to do that is to take the difference between this curve and this curve. So here we have our radius is e to the x plus 3 minus 3, which is just e to the x. And we have to do this because we want to ensure that we have an accurate representation of the distance from the axis of revolution to the curve. Now when we go to fill in our integral, we have volume equals pi times the integral from 0 to ln7 of e to the x squared dx. This is pi times integral from 0 to ln7 of e to the 2x dx because of exponent properties. But now we have to make a substitution because we don't know how to integrate this just here. So I'm going to let u equal 2x. So du dx equals 2. So du equals 2 dx. To get 2 dx here, I'm going to multiply by 1/2 on the outside of the integral and multiply by 2 on the inside of the integral. And so now when I make these substitutions, I get pi times the integral from x equals 0 to x equals ln7 of e to the u du. And now it's just a matter of evaluating the integral. So this becomes pi times, so integral of e to the u is e to the u. So e to the u evaluated from x equals 0 to x equals ln of 7, which is pi times e to the 2x evaluated from 0 to ln 7. And this is pi times e to the 2 ln 7 minus e to the 0. And we can write this as pi times e to the ln 49 because of ln properties minus 1. So e and ln cancel. So this is pi times 49 minus 1, which is 48 pi. And that's the volume of the shape that's formed when this area is revolved around y equals 3. For our third example, we're in terms of y. We're asked to consider the area bound by f of y equals y squared, x equals 0, and x equals 3. So let's consider it. I'm going to draw these on the plane to show you what it looks like. So here's y squared, this is x equals 0, and here's x equals 3. So we're asked to consider this area. We're told to find the volume of the shape generated when this is revolved around the y-axis. First, let's find our bounds of integration. I'm going to do this by setting y squared equal to 3 and finding the points of intersection. When I set these equal to each other, we can very easily see that our intersection points are plus or minus square root of 3. So what that means is here is negative root 3, here is positive root 3, and we're going to integrate between these y values. Now let's determine which method we're going to use to find the volume. Well, in the interval negative square root of 3 to square root of 3, this area doesn't touch the y-axis or our axis of revolution at all points in this interval. So we have to use the washer method. Now we have to find our big radius and our little radius. It's really important that we do this always with respect to our axis of revolution. And so you'll see what I mean. Here's our axis of revolution, and we have to find the outer radius with respect to this axis. So what you do is, you imagine you're standing on this axis and you're looking this way towards the two curves. So whichever one is further is our outer radius. In this case here, it's x equals 3, so our outer radius is 3. Similarly, when I stand here and look towards the curves, the closest curve is y squared. So our little radius is y squared. Knowing our integration bounds and our radii, we can now do the integral. Here's everything plugged in, and now it's just a matter of evaluating this. I'm going to begin by applying the squares. And now I'm going to use the power rule to integrate this term by term, like so. And then we're evaluating this from negative root 3 to positive root 3. And I'm just going to use a calculator to find this value. So the answer to this is 72 pi times the square root of 3 over 5. And this is the answer to our problem. So we're asked to consider the area bound by y equals x squared minus 4 and y equals square root of x minus 4. Let's consider it. We're going to draw the two curves on our plane and see what they look like. Okay, so I've drawn x squared minus 4 and square root of x minus 4. And here's what they look like. And so now we're asked to revolve this area about y equals 2. Let's first establish which method we're going to use. This area does not touch our axis of revolution at all, so we're going to use the washer method. Now let's find our bounds of integration. And I'm going to do this by setting the two curves equal to each other and finding their intersection points, like so. From here, the minus 4's cancel out. And then I'm going to square both sides, like so. And I'm going to subtract x to this side. So dividing by x here will make you miss out on a solution, and then you only have 1 point, which doesn't make sense. Here, I'm going to factor out an x. And from here, we can see that x equals 0 and x equals 1. So these are our intersection points. Now we have to find our big radius and our little radius. Remember how I said in the last example, we always want to find these with respect to our axis of revolution. When I stand on this line and I look this way towards the curves, the outer curve that I see is this, or x squared minus 4. But x squared minus 4 isn't the true distance from here to x squared minus 4. To find this distance, I'm going to take the difference of 2 and x squared minus 4. Like this, that gives me 6 minus x squared. Similarly, our little radius is square root of x minus 4 because when I stand on this axis and I look down, the closest curve is square root of x minus 4. But again, that's not the true distance from this curve to the axis of revolution. So we also have to find this difference with square root of x minus 4, like this. And that gives us 6 minus the square root of x. So now that we have our integration bounds and our radii, we can just do the integral, like so. What I'm going to do is I'm going to expand these squares, and then I'm going to do this subtraction. This is what you have left after you distribute the negative and perform the subtraction. So now I can just integrate term by term, like so, and I'm going to evaluate this from 0 to 1, which gives me this. Oh, by the way, there should be a pi multiplied to all of these. And this is equal to 37 over 10 pi. And this is the answer to our problem.